Welcome to basic summation properties. So we're just going to run through some very basic sums and facts, and then we'll do some examples with specific numbers. So our first summation is the summation from I equals 1 to n of a constant c. And this is just adding n copies of c together. So we just wind up with n times c. So for example, if we wanted to do the sum from I equals 1 to 25 of 4, then this would just be 25 copies of 4, or 100. Next up, let's look at the sum from I equals 1 to n of I. So this is like 1 plus 2 plus 3 plus 4 plus 5, going on until n. It turns out that this is n times n plus 1 divided by 2. So for example, let's say we wish to take the sum from I equals 1 to 50. Actually, let's not do that large. Let's do a smaller one. Let's just go from I equals 1 to 20 of I. So this is 1 plus 2 plus 3 all the way up through plus 20. Then in this case, we have n is 20. And so we would do 20 times 20 plus 1 all over 2. So this is essentially 10 times 21, or 210. And then next up, let's do the summation from I equals 1 to n of I squared. It turns out that this is n times n plus 1 times 2n plus 1 divided by 6. So for an example, let's go ahead and do the summation from I equals 1 to I equals 1 to 12 of I squared. So for this, our n is equal to 12. Right? Again, n is just where we're stopping at. So n is equal to 12. So this should be 12 times 12 plus 1 times 2 times 12 plus 1. And then that whole thing divided by 6. Or 12 times 13 times 25 divided by 6. And if we do that, we wind up getting, let's see, that would be essentially 12 divided by 6 is 2 times 25 is 50 times 13 would be 650. And so the summation from 1 to 12 I squared is 650. Assuming I did my arithmetic correct. All right, from here, we have the summation from I equals 1 to n of I cubed. And it turns out that this looks very similar to the summation from I equals 1 to n, but then we square our results. So this is n times n plus 1 divided by 2, and then the whole result squared. So for an example, if we wish to find the summation from I equals 1 to 5 of I cubed. Here my n is equal to 5. So I am doing 5 times 5 plus 1 divided by 2, or 5 times 6 divided by 2, which is 15, and then squared. And we wind up with 225. So we could just do a quick check. 5 cubed is 125, plus 4 cubed is 64, plus 3 cubed, we're adding 27. So 64 plus 27 would be our 91, plus 2 cubed would be 99, plus 1 cubed is 100. That 100 plus the original 125 is indeed 225. So this is just a faster way of finding the summation of I cubed from, oops, this should be from I equals 1 to 5, from I equals 5 to 5, from I equals 1 to 5. The next couple properties will allow us to essentially take polynomials in terms of I basically, and then simplify. So if we have the summation from I equals m to n of some ai plus or minus bi, we can split this as 2 summations. So this is the summation from I equals 1 to n of a sub I, and then plus or minus the summation from I equals 1 to n, sorry, I equals m to n of b sub I. So essentially we can split sums across addition or subtraction. Next up, we have the sum from I equals m to n of c times ai. We can go ahead and pull out our constant c and then just have the summation from I equals m to n of a sub I, that whole summation multiplied by c. So essentially, note if we have a summation from I equals 1 to n of a sub I, where a sub I is some sort of polynomial in terms of I. As long as the highest power is a cube, we can now go ahead and evaluate the sum. So a polynomial of degree 3 or less, we can now evaluate any of these sums. I apologize if you can hear my mother-in-law talking in the background. So for an example, let's say that we wish to do a summation from I equals 1 to n of 2i squared minus 3i plus 5. Well, we can go ahead and split this. Oh, sorry, not 1 to n. The summation from 1 to, let's do from 1 to 10. 2i squared minus 3i plus 5. Well, by the last two properties, this is equivalent to 2 times the summation from I equals 1 to 10 of I squared, then minus 3 times the summation from I equals 1 to 10 I, and then plus, we could do 5 outside if we want, or we can just leave the 5 inside, since we do know the summation from I equals 1 to 10 of the constant 5. So we have n equals 10 for each of these. And so this first one, we will have 2 times. The rule for I squared was n. I apologize. I'm going to see if I can get more quiet. So we had the rule for I squared was n times n plus 1 times 2n plus 1 all over 6. So we have 10 times 10 plus 1, or 11. And then 2n plus 1 would be 21. And that all is being divided by 6. So that's our summation I squared if we're going from 1 to 10. Then we will subtract off 3 times, and then the summation of I, the rule was we did n, so 10 times m plus 1, or 11 divided by 2. And then the rule for summation of a constant, we just did n times the constant. So this last one would just be 10 times 5. So if we go through and add all of this up, we wind up getting that this is equal to 655. So we now have the ability, we could have gone as high as I cubed in our little polynomial in terms of I. We now have the ability to do any of these summations. All right, and now this last one, basically what we have is if we go from I equals m to j of a sub I, and then we add on the summation from I equals j plus 1 to n of a sub I, that we can just tag these together and it becomes the summation from I equals m to n of a sub I. So essentially what we're seeing for this is, for example, if we wanted to find, if we had the summation from I equals, say, 1 to 3 of a sub I, and then the summation from I equals 4 to 10 of a sub I. Well, this first summation would be a1 plus a2 plus a3, and then we would have from the second plus a4 plus a5 all the way up through plus a10. We just have the whole set from I equals 1 to 10 of a sub I. So where this comes in handy is we can rearrange this formula. So let's go ahead and use 1 for our special case. So just note, if we use m equals 1, then what we have is just in general the summation from I equals 1 to j a sub I plus a summation from I equals j plus 1 to n a sub I is equal to the summation from I equals 1 to n of a sub I. And if we subtract that summation from 1 to j, this is equivalent to saying that the summation from I equals j plus 1 to n of a sub I is equal to the summation from I equals 1 to n of a sub I minus the summation from I equals 1 to j of a sub I. So this will let us find some partial summations where we start at something other than I equals 1. So for example, let's just do the most basic. If I wish to find the sum from I equals 5 to 15 of I, well, this should be the same thing as taking the sum from I equals 1 to 15 of I, and then removing the 4 terms we don't want. So namely, from I equals 1 to 4 are the ones we wish to remove. We want starting at 5. So we could find these two separately, and we know how to find those two. So this first one, we're looking at n equals 15. And so we would do 15 times 15 plus 1, or 16 divided by 2 for the first summation. The second one, we're looking at n equals 4, still summing I. So we would do 4 times 4 plus 1, or 5 divided by 2. 8 times 15 is 120. And then we are subtracting off 10. And we wind up getting that this sum is 110. So we now can figure out any sum from I equals m to n, as long as the a sub I is a polynomial in terms of I of degree 3 or lower. So this will come in handy as we go about doing our summations with rectangles and areas of rectangles. As we do more and more rectangles, we'll have lots of things to sum together, but we can use these rules to sort of avoid having to add them up one by one by one, like we did in our initial Intro to Riemann sum video.